Okay, so last time we were looking at this notion of interlacing. So it was defined like this. So you have so we're defining the notion of a common interlacing. So we started off with this idea that there's an n degree d univariate real polynomials, and we assume that all of them have positive leading coefficients. That means that as x goes to infinity, all of these things go to infinity. Okay, all these polynomials go to infinity, and they're all real rooted. So then, they are said to have a common interlacing. If the sequence of numbers d plus 1 numbers alpha 0 to alpha d arranged like this in descending order. So it's not strictly descending necessarily, it's just descending order. Such that if you look at the d roots again in descending order of the f of any fi, so you count multiplicity and again you arrange in like weakly descending order. So no, not necessarily strict because the roots may be repeated. Then they interlace in the sense that the roots, the d roots lie between these d numbers in this way, that the first root lies between alpha 0 alpha 1, second root lies between alpha 1 alpha 2. Again, not strict, everything is here is non-strict, like, and so on, right, up till the dth root here lying in between alpha d minus 1 and alpha, right? Okay, so that was the notion of a common. And so what is common about it? That the same alpha 0 satisfies this property for every polynomial at the same time. So this alpha 0 is not allowed to depend upon the polynomial. So the alpha 0, alpha 1, these sequence is not allowed to depend upon the polynomial. It's one sequence, and it has to do it for every. So this is a very special thing. I mean, like if you take arbitrary polynomials, usually this will not be the case, right? I mean, the roots you can take polynomials whose roots are like, so one polynomial might have root 1, 2, 3. The other polynomial can have roots 7, 8, 9. They don't interface. So this is constraining the polynomials a lot. Another way of defining this interlacing is following, that you just define the root interval. So you have the sequence of roots. So you just define the jth interval as the jth interval is between so it's between between the jth entry and the j plus 1th entry. That's what this interval is. And of course at the boundaries you define everything from minus infinity to the first one, and so on. Right. And so then they have a common interlacing if and only for every j. So every j between 0 to d, the corresponding intervals corresponding to each of the polynomials have a non-empty intersection. So this is easy to see that it's the same thing. Okay. So the thing we wanted to prove is that if f, so we proved is that if the sum of polynomials f, sum of fi, I don't know 1 to n, and if the fi's have a common interlacing, and this f has a largest root at most delta, then there is one of the fi's which also has largest root at most delta, gamma. So if the sum has the largest root at most gamma, then one of the fi also has largest root at most gamma, provided the fi's have a common interlacing. Without the common interlacing, this can fail, and it's not hard to construct. That's where it fails, like small degree polynomials. Okay, and this proof was sort of more or less sign chasing. So this was fine. So then the question was, how do you prove common interlacing? And this we looked at this lemma, which is quite old, but has been proved several times by several people. And the proof we did was by Shudnowski and Semmer. And this it says the following: that suppose you have two polynomials f and g, not n, just two, which are again degree d and with positive leading coefficient. And if you suppose that every positive linear combination, every non-negative linear combination of f and g is real rooted, which is the same thing as saying that every convex combination of f and g is real rooted. So if that is the case, then f and g have a common interlacing. So this is reducing finding a common interlacing to proving that a certain family of polynomials is real rooted. Okay. So there are two things. One is why pairwise. So one easy thing to show is that if you have a collection of polynomials f1 to fn, and every pair of them has a common interlacing. So again, f1 to fn, all of degree d and all with positive leading coefficient. And suppose that every pair of them has a common interlacing, then all of them together also have a common interlacing. So this is not a hard thing to prove. So it is enough to do this in the pairwise setting in some sense. Okay, so yeah, so then we did a proof of this more or less. So let's not worry about the proof. We finished the proof that this is the case. So basically, if you have polynomials f and g, and if every non-negative linear combination of them is real rooted, then they have a common interlacing. This also implies that if you have f1, so by the same thing that you just said, it also implies that if I have n polynomials and every convex linear combination of them is real rooted, then all of them have a common interlacing, right? Because if every convex combination of the n polynomials is rooted, then for every pair also that's true, and so every pair has a common interlacing. And then, as I said, if every pair has a common interlacing, then the full set also has a common interlacing. Okay. So let me just write this out. That's a remark. F1 to Fn are degree D with positive and height positive leading coefficient, and then the following are equivalent. For every I j, fi and fj are common interlacing. F1, F2, F5. Okay. So this, yeah, I think Siddharth pointed out that it's Helly's theorem. Yeah, and yeah, it is a consequence of Helly's theorem, but you can also just prove it even if you don't want to use Helly's theorem. It's just changing the definition. You basically just start with this interval definition and then just proceed from there. Okay, so this thus F1 Fn are equity are positive leading coefficient and such that every non-negative linear combination Okay, so this follows, right? Just from the lemma and this remark. Okay. So now let's look at another consequence of this. That's the one that we'll be using, which is the following. Now, so this is what MSS called the method of interlacing families.
So this Piyush, one thing,
Yeah.
to prove this kind of results using the interlacing business was done by MSS first, is it?
Which kind of results? The Ramanujan graph.
So certainly for the Ramanujan graph, they were the first. But I'm just saying in general, proving any combinatorial kind of statement using.
No, I mean, well, the
but you said this
Heilmann-Leib is also by interlacing. So, so the original proof of, in some sense, the original proof of the Heilmann-Leib theorem is also via constructing of interlacing. It's sort of like, well, it's sort of via interlacing in the sense that you keep constructing polynomials whose roots interlace one after the other so that they all are real rooted. So the fact that the matching.
They didn't coin this word interlace. They didn't explicitly mention these.
No, so the word interlacing and all of this is older.
Okay.
Yeah. So their main contribution is, in fact, the connection between real stability and so I said it. This whole theorem that we have proved is this proof is due to Chudnovsky's theorem, and the idea is much older. Like the theorem has been known for a long time. Their idea was the thing is, okay, so if you have an interlacing family, you have this kind of thing. So we'll see that one thing is that one of the ideas was that to do a specific kind of family of interlacing polynomials, and then of course choosing the right family. So both of those were crucial to get through the Ramanujan.
So that means basically, although the interlacing method was sort of known, it was not clear how to use the interlacing method for Ramanujan graphs.
Yeah. And that's anyone even tried. Yeah.
No, huh?
I'm not even sure if anyone had even tried that.
Right. Okay.
So this exchange of expectation idea might have been there, right? That you can basically do this probabilistic method like thing if things interlace.
Yeah, so this is, I think, so I might have been there, but I also haven't seen an explicit example.
No, but yeah, so this Heilmann-Leib paper you already said. I mean, this.
So there, the interlacing thing occurs in a different context. There, it's like you have to prove the matching polynomial is real rooted.
No. I'm just saying that the first calculation or one of the early calculations that you did, where you showed that the expected polynomial is the matching polynomial.
Yes.
Right. That is also.
Yes, that is also an old result. That is goes at least as far back as Godskill in the 80s or maybe older.
Oh, then I'm really perplexed. And you're saying the interlacing method was also there. Somehow people still miss the idea of.
No, so idea of interlacing was there. So we'll see that there are more things.
Okay.
So even constructing the right interlacing family is not clear.
No, what I'm saying is like, I mean, of course, we have to say hindsight is 2020. And that's
yeah.
But the point is still, I'm just saying, at this point, from what you have shown, this is all you are possibly about to start the MSS part, right? But now that you have set up this ground, it does seem like it's very reasonable to say, hey, can the interlacing method help us here, right?
Yeah. So the thing is, what were people using the interlacing for? So what was Chudnovsky's theorem or Heilmann-Leib using it for? They were proving it sort of using it often to just prove real rootedness, because I mean, so when you construct polynomials, you will show that there's a degree D polynomial and there's another degree D plus 1 polynomial, and the roots of degree D polynomial interlace the roots of degree D plus 1, or the signs interlace. Then you have also proven that the other guy is also real rooted because you have shown the right number of sign changes. So that was how both Heilmann-Leib and Chudnovsky were using the idea of interlacing. So to use it for bounding the maximum roots is sort of one of the new things. So by the way, so it's not like, so I already showed you one result, one of the simpler observations. Again, simpler in hindsight. This is also from MSS. This lemma that this one that. If you have a family of interlacing polynomials, you take the sum. The sum has the largest root at most gamma, then one of them has a root at most gamma. This is also MSS.
Yeah, I think this
this
is
was an
really the
observation of
field
MSS.
Yeah, sorry.
No, I was just saying this the root thing. If the expected polynomial has its root is bounded. No, suppose that.
Yeah, so you have expectation, the root is bounded, and all they have common interlacing. Like all the realizations have a common interlacing. Then the maximum root is also bounded.
So this is due to MSS.
Yeah, at least in explicit form, yes. I mean, there might have been some pretty good knowledge, but yeah, but I don't think I have not seen anything.
Okay. So this observation makes it, once you make this connection, then it becomes very natural to see. Yeah, I mean the fact that I mean the matching polynomial root is bounded. This is
No,
right?
so the connection between matching polynomials and the root and so on, that was all very well known. There are many reasons for that. So one comes by this so-called notion of universal cover. So the thing is that, okay, so there's a good reason to believe that the spectral gap of the so-called the infinite deregular tree should be the right answer in some sense. And so of that graph, and that graph has spectral gap exactly 2 times square root d minus 1. In fact, that's how the Alon-Bopanna proof goes. If you look at the Alon-Bopanna proof, what they're trying to do there is to sort of mimic the infinite Dirichlet tree in at least one of the proofs. So, and then, so what does that have to do with the matching polynomial? And this is an old result of God's, that the matching polynomial of a graph divides the matching polynomial of its so-called self-void which is the universal, which is
A subgraph of the universal.
Sorry?
It's a subgraph of.
It's a subgraph of the universal cover. Yeah. So these kind of things were so there were reasons to believe. So all these connections were all known, like the matching polynomial, the spectral gap of the root of the matching polynomial connect. Why does it connect to the root of, like, it can connect to the root of the spectral gap of the universal cover. So all of these things, there were interesting connections already known. So we'll see it, like it's also a non-trivial thing to actually come up with this family. So the point is, there's a bunch of these FIs. So the question is, what are these FIs? And
No, I mean I am not disputing that, but I'm just sort of saying, you said that nobody even tried coming up with interlacing.
Yeah, so that is true. So no one tried to prove it using this kind of, like, what you would call it, like very geometric kind of idea of just chasing signs. Yeah, that is true. And likely it was not because they were unaware of this idea, but because they were probably unaware of how to come up with this, what the right FIs are.
Okay.
Yeah, that would be my guess. Okay, so yeah, okay. So what is this? So this is essentially extended version of the lemma that we proved already. So it will just slightly relax the condition. So notice what is the condition here? Condition here was, you have a sum of FIs, all of them to have a common interlacing, and then you have this. Okay. So we'll have that under certain special conditions, you can relax this a little bit. So the idea is this. So now suppose that your so let us say that our sample space is some sample space which is like omega 1 cross omega 2 cross omega n, right? And suppose that, and these are all finite sets. Suppose that for every omega in omega, we have a degree d polynomial, univariate polynomial, so which I'll just call f omega x, which also you can write omega 1, omega 2, so until omega n x, with we have with real roots and positive leading coefficient. Okay, and suppose the following are true. Suppose 1, there exists distributions, probability distributions mu I on omega I such that the expectation over the product, the product distribution. So this polynomial, which let me define this as f, the empty set. So, or rather the empty string. Yeah, I don't know how to write it. So let me draw this. F0 of x is defined to be the expectation over all omega taken from the product distribution. Has maximum. So this is a hypothesis. So it has maximum root gamma. Okay. And the second thing in the hypothesis is that for all probability distributions mu I on omega I, this E f omega x when omega is sampled according to is real rooted. Okay. Then there exists one of these polynomials, f omega x is maximum root at most. Okay, so what's the, so let's just check. So what's the thing? So now we have a bunch of polynomials. Again, we have that the expectation of these has maximum root gamma, but the expectation is of a special form. It's not some arbitrary expectation, it's expectation with respect to product distribution. And we also assume that for every product distribution, this the polynomial that we get by taking expectation is real rooted. So under these two conditions, we get that one of the polynomials f has maximum at most gamma. Now we are in business. So in our application, what would this be? What would these omegas be?
So Piyush, how is this sort of? I'm just trying to appreciate the speciality of this. Meaning, how is this a bit more specialized than the informal statement that you said right at the beginning? If we could, if we knew that all of these were real rooted and there was an interlacing.
Yes. So the thing is, how do you find the interlacing?
Oh, okay.
So to find the interlacing, common interlacing, we would have had to prove it for all averages of those polynomials. So this thing, maybe you can't do it for all averages. Maybe you can only do it for product distributions. So let's say we want to apply the original one. Okay. So, or the remark that I mentioned, right? So then what would we need? We want a common interlacing. How would we get a common interlacing? So if you look at the remark that we had, that would require, so that would need you that I don't know if I mentioned it explicitly, but the point would be that you will have to show that every non-negative linear every non-negative linear combination of the Fi is real. Okay. So this might be too much to ask. Okay. So instead, now what we are asking is only that the average, not all combinations, but only those that come from product distributions be real. Okay. And that will still be sufficient. Okay, so that's the difference. So the difference is that difference from previous version. Two asks for real rootedness only of product distribution averages. Not all averages. Okay, so that's the.
Piyush, I just joined it. Sorry for that. So just omega is to take sample from the product distribution. That symbol means, right?
Yes. Yeah, that symbol means so yeah. So that is sampled from. So there's some distribution here. Omega is sampled from that distribution.
Okay, and then you are taking the expectation over the polynomial over.
Yeah, so the polynomial, because them as vectors, we can do. Okay, so that's the and the proof, is, so given the result, the proof is not so hard given the statement. Okay. So yeah, so it's sort of by when one thinking of it is by induction or whatever. But before that, let me say what would it be in our setting. So in our thing, these omega is are just binary, like 0, 1. And the nu is a uniform distribution. These fm omega will be the urgency, would be this, if you remember this matrix AS, they will be the characteristic polynomials of those AS. And this f0x will be the matching polynomial. And so we will have to prove that under every averaging of those characteristic polynomials, you're still fine. That's the kind of. Okay, but let's first prove this. Yeah. So any hints on how we should go about this?
Yes, so if you consider the tree and look at the nodes below, the children of each node.
Yeah, so that's that's how they wrote it in the early version. But I mean, so you don't have to really do all that. So that's a good way of structuring the argument. But I mean, the basic point is just this: that just look at this f0, right? What is this f0? It's a mean over various things, but in particular, it's also like a. So what is this f0? So just define. So define f s1 s2 so on till sk to be this polynomial where you just sample. So so you just take the mean of s1 to sk and then omega k plus 1 all the way till omega n.
Sorry, Piyush, what is this S1 to SK? These are those signs.
So let me just so what is this? So I'm just defining these things. So what are these? So these each SI is in omega I. So earlier these polynomials were only defined for when I specify all the n entries, right? So I'm just defining some partial version of that, which is just you just average over the other entries.
Okay.
Okay. So where these omega I is sample quantum independently. right? So in particular, that's why I was calling it the empty string. This is exactly the expectation. Omega, the product distribution. Okay, good. So this is this. So now the point. So let us see. So what is f0? What is this f0? So this f0 is because of this product distribution thing. It's just so it's summation mu1 of alpha of f alpha, right? Where alpha is in omega 1 because of the product definition. Right?
I'm a bit confused. No, mu1 is the probability distribution from the first set, right? No, wait.
Sorry, I probably.
Yeah, it's okay.
No, yeah, that's fine. This is just this okay. Right? So this is fine, right? So you fix the first coordinate, then you're averaging over the rest of the things.
Correct.
So then you have to do this. Okay. Right. So so we know that this f0 has this f0 has maximum root at most alpha, right? So gamma, so max root of. Right. Now, can we claim that these f alphas have a common interlacing?
Yes.
Yeah, so why is that?
So take any probability distribution on the f alphas and and consider the following product distribution where the first coordinate is distributed according to your given probability distribution and the remaining are uniform.
Right. So now consider the probability distribution. So let mu1 be an arbitrary distribution, so probability distribution on omega 1. Right? Consider this this distribution mu1, and then the rest are just mu2. Just the mu1s. Okay. So then, what is this expectation of when omega is sampled according to this mu1, mu2? It's a product distribution. So when I sample according to when I do this is real rooted by 0.2. But then this expectation it's exactly by definition just mu1 alpha f alpha. Sorry, f alpha. Okay. So this means that for every convex combination of the f alpha is real rooted. So what does that imply?
They have interlacing.
Yeah, so f alpha have a common interlacing.
Previous
yeah. But what does that mean? At least one of them must have. So there exist such that max root of f alpha is less than gamma. So this is by the main interlacing lemma, by the first interlacing lemma that we proved. Okay, good. So we have fixed one coordinate and found a polynomial which has root alpha, and this you can do inductively now. Okay. So let's see. Suppose now that suppose we have found alpha 1, alpha 2, so on up to alpha k, such that f alpha 1, alpha 2, alpha k max root is less than gamma. Okay, but then this f alpha 1 all the way up to alpha k is just nothing but summation mu alpha mu k plus 1 alpha f alpha 1 all the way up to alpha k, and the last one is alpha. Maybe let me use another thing, beta of x. Okay. Beta is in omega k plus 1. Okay. Take any distribution. I mean, I'm just repeating the same argument. So take any distribution mu on what?
On the children of alpha 1 to alpha k.
No, on
Omega k plus 1.
Yes.
Mu on omega k plus 1, and and consider the product distribution. So what should, so now this is maybe the only tricky thing. What is the product distribution that we should consider?
So alpha 1 to alpha k on okay. Yeah, so alpha 1 to alpha k fixed constant probability distributions on the first k coordinates.
Yeah.
And mu on the k plus 1 coordinate and uniform on the remaining coordinates.
Yes. Yeah, so mu on the remaining.
I didn't get why with that only that choice.
Yeah, so let's see why we need only that. Why we need that particular choice? Because so we need a product distribution. Sorry, Siddharth, I can't hear you.
Yeah, I think Siddharth is trying to say the same thing. Why is it uniform on the remaining? Why is it
not uniform? Mu.
Yeah, because Srijato said uniform. I think.
Yeah, mu
I
uniform actually.
Yeah. Because, in our setting, mu will be uniform, but mu need not be uniform. Okay. So let's call this distribution something. Let's call it tau.
I was saying.
Yeah.
Yeah. I was saying that the second point is an overkill, right? You didn't need it for all product distributions. Only these. I mean, you get to fix the first few coordinates.
Yeah. You get to first pick the first few coordinates to Dirac delta.
And what is this new panel? Why do you need sort of? I mean, the first are delta, Dirac delta, then.
Because we have to get a common interlacing. So how will we get a common interlacing? By showing that every convex combination is real rooted. Yeah. So then by point 2, the expectation of this f omega x omega according to tau is real rooted. Okay. But what is this expectation? So this is where sort of we need this particular construction though. So what is this thing? So this has to be, so just by definition, because the first k coordinates are fixed, the kth coordinate is k plus 1 coordinate is moving according to nu, and the rest are just moving according to mu. So this whole thing is exactly summation nu beta f alpha 1, alpha 2, alpha k, beta x. Yeah. So the reason we can drop the rest is because the remaining are sample according to mu. Beta n over k plus 1. This implies that f alpha 1 alpha k beta as beta over k plus 1 have a common interlacing. So yeah, so it's exactly the same argument. So I could have just have done this argument and then said that do induction. Right? So that's what. So this implies that so why is this? Because we have proved it for arbitrary any distribution. That's the important thing, right? A common interlacing, and therefore there exists beta omega p plus 1 such that maps root alpha 1 alpha k beta is less than or equal to max root f alpha 1 all the way to alpha k, which is less than 1. So set alpha k plus 1 equal to beta. So by induction, we find s1, 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 s1. Okay. Induction. Or by just by repeating this n times. Okay. So yeah, so now our goal is so in our string, what would be these things? Yeah, so let's come back to yeah, so back to so by the way, so any questions about this?
I can't hear you.
No, I was quiet just to wait for questions. Okay, so if there are no questions, then let's proceed to applying this.
So, Piyush, here in this, in earlier, the lemma, had it worked for all kind of roots, you would have obtained.
Your voice is not clear. Okay. Okay. Yeah. So now, so now, yeah. Okay. So, so let's come back to our the Ramanujan graph question. So we had done some reductions already on that problem, right? So okay. So we had done some reductions already on that particular problem, and we had the following thing. So we had this notion that, so recall the setup. So the setup was, so G V is an undirected deregulator graph. A is the adjacency matrix. S, so S in -1.
The screen is not visible.
Your screen share gone.
Yes, something went wrong. Oh no. I don't know what went wrong, but I lost whatever I had written there. Okay, so setup. So setup was that G is undirected, degree at most D. Okay, and then we had this this thing that you have AS. So sorry, so A is adjacency matrix. Of G, and for assigning of the edges, so each edge is assigned a -1 sign. We defined AS to be the matrix, with the same matrix where ASIJ is equal to AIJ is equal to minus ASIJ if ij is in the edge and the the sign of the edge is -1, and it's equal to ASIJ. Sorry,
AIJ, right?
yeah,
Yes.
AIJ otherwise. So you just change the signs of the entries corresponding to those edges. So it's AS is still symmetric because you change the entries of both the signs, but you change the signs of entries corresponding to and yeah, the signing of these. And then what we wanted and what we showed that, and we showed that for to prove existence of an infinite family of irregular bipartite dimension expanders, it is sufficient to bound the max root of one of the As, in the sense that we want to show that there exists S such that max root is for any G of degree agnostic. For any g of degree at most t, there is an s such that is the case. Then you have what we want to show is that for any g of degree at most t, there exists yes. Okay. Sorry, what is max root of x? Max eigenvalue, right? Which is equal to the max root of the polynomial, the determinant of xi minus as. Okay. We also showed that the expectation when S is uniform minus 1, 1 to the n of det xi minus as is what? Is the has max root at most. Okay. So okay, so all we have to do then is to the first so this is the first step. So do this. The first condition of the method of interlacing families is already satisfied. What is this thing? Omega with so with omega I is just being minus 1, 1, mu I to be the uniform distribution over that. Right. And that's it. And f omega s to be that. So there are some other conditions also, right? Which are all real rooted. Why?
Characteristic polynomial of a symmetric matrix.
Yeah, and they have positive leading coefficient. Why?
It's monic actually.
Yeah, so this is just by expanding the determinant, positive leading coefficient, and one more thing, right? And all at the same degree. Okay. So the first condition is fine. So the crucial thing now is the second condition.
Sorry, the degree was needed?
Yeah, because well, technically it's not needed, because when you say common interlacing, that already implies that the degree cannot differ by too much, by at most 1, depending upon how you define interlacing. But for simplicity, we always assumed in all our proofs that the degrees are the same. So interlacing by itself would imply that degrees cannot differ by too much. Right? In fact, the way I define interlacing, it will actually imply that degrees have to be equal, because there were d roots. But if you define interlacing in a slightly weaker way, you can also get d and d minus 1. So like differ by 1 at most. But yeah, so you have to be more careful in some of the arguments. But we just assume that all the degrees are the same.
Piyush, in the second condition already subsumes part of the first condition of real rootedness, right?
Yes.
Okay.
Well, yeah, I mean the technically the first one does not require, like there's no requirement that so it's only saying that The expectation thing has maxed out at most this. There is, so remember in the lemma we never use or never required that the sum also has to be real. But the hypothesis implies that the sum also will be real because of the common interlacing thing. But it is not needed, the proof.
Yeah.
Okay. So okay. So this is another thing is to do the second one, which is yeah. Okay. So we have to do the second condition. So for this, actually, we'll prove something slightly general, and to show that, well, first show that the general statement implies the current statement, and for that we'll have to slightly restate what AS looks like. So so what is this AS, right? So, or what is even A? So so let me just write something and then you can check. So so we have that this so let me define for each edge. So for each edge E equal to U, define two vectors. So one is the what we call the VE plus. V is probably not a good. So let me concentrate. W plus. So WUV. So what is this? So this is okay. So this is the matrix. So this is, sorry, it's not a vector. It's a, right now the way I draw it, it's a matrix. So the vector is this such that now this W plus UV times W UV plus transpose is a matrix such that it's UU entry, VV entry. So this is U, this is V, this is U, this is V. This is one, this is one, this is one. Everything else is zero. Okay. And similarly define WUV minus to be 1U minus 1V. It doesn't matter which sign doesn't matter, because the crucial thing is that we'd only be looking at the matrix and then the sign goes away. And now this is what? So now the off diagonal entries, this is still one. Okay. So so now the point is that these A and ASs look like this. So AS is just the degree matrix. So the degree matrix of G, diagonal matrix whose entries are the degrees of the corresponding minus. Yeah, and plus summation WUV. So let me just call this WVS. So where this WE plus minus is just defined to be WE plus minus times WE plus minus transpose. So we just sum it up. So for each edge, we'll get the corresponding ones or minus ones as it is. The degrees get added up, so the whole thing looks like this. This is fine.
Yes.
Okay, so let me not belabor this thing too much. The point is that this whole so what is this AS? So what is what I want to think of is something slightly more general. So, I will not immediately write on the translation, but so what we will do is we will look at following general case, following general situation, and then later on we'll come to this. So we have some we have some large numbers. So let me just use the notation from. Yeah. So we'll have some distributions. So we'll have distributions. Let me call them mu1, mu2, so on to mu n on finite sets omega 1, omega 2, so on till omega m of n-dimensional vectors. Okay, so each omega I is a collection of finite set of n-dimensional complex vectors. Okay, in our thing it will always be real, but yeah, let's just think of this. Okay, and yeah, right, and then the polynomial you want to look at is, or rather, let me use so we have finite sets. Okay, and we look at the following, and for let mu1, mu2, mu1 be probability distributions on the arbitrary probability distribution. and we define we then want to we will show that so-called the mixed characteristic polynomial what is this mixed characteristic polynomial? It's the expectation of det of xi minus summation vi star. So star is complex conjugate transform I going from 1 to m, where this v1, v2, so on, this tuple is sampled according to the product of the new i's. Maybe this is not. Yeah, I want to use new because that's what we're using. Maybe we can call it so no matter what these vectors are, no matter what these distributions are, as long as you're taking a product distribution and then taking expectation, the so-called mixed characteristic. So you take the characteristic polynomial of the matrix form, okay, and then take the expectation of this is real rooted. So notice that it's
sorry, Piyush, what are these UIs? I got a bit
arbitrary. So that's what I'm saying. So these UIs are just sampled from these new I's. So let us just recap the setup. The setup is we have some collection sets omega 1 to omega n. What are these sets? Each omega I is a finite set of vectors from C to the n. It's a finite set, it's not a vector space. It's a finite set of vectors. Okay, so what would be these vectors? So I'm not giving the full translation, but these vectors will be things like this, either 1u plus 1v or 1u minus 1v, things like that. Okay, so except for this du business, you can probably see that this is already related to what we were doing earlier, because distribution on AS is exactly like putting a distribution on these vectors and then choosing those vectors and then summing them up. Right? So if I forget about the D part for now, for example. What is this? So suppose our omega I was exact. So I had one. So that's why I call it M. So omega I was just these two vectors, 1u plus 1v and 1u minus 1v. Where so for each edge omega E is exactly these two vectors. And then I'm looking at an arbitrary product distribution on this. So then, except for this D part, we're exactly looking at the
sorry? You know, but this M, the yes. M that you have, it could be arbitrary also, right?
It could be very large, yeah. So in our application, it will be equal to the number of edges in the graph. So notice, but here, so all of these are independent. N the number of vectors, M the number of spaces, and the number of vectors inside these things is also I'm just assuming it's finite, no bounds or anything. In our application, it will be 2, but
Piyush, so here, like in the earlier case, we analyzed always the distribution with half being +1 and half being -1. So when we expanded this determinant,
we'll have to remember that we have to prove things for arbitrary product distributions. Now we cannot have that luxury.
Yeah. No, I'm just trying to understand this this thing over here. And like earlier, we had done it for a very special case, right? When everything was uniform.
Yeah, so we had proved. Yeah, we had actually just shown that when it's a half, that whole thing became the matching polynomial, and we had already a different proof that it is. So we'll have to do a very different proof that this thing is, which will also prove in fact that the matrix the matching polynomial is very stable, because
No. So I wanted to know. So earlier it was simple because when we expanded this determinant, if most like very few things in the sum could survive.
Yes.
When we expanded the determinant along permutations, but now everything can possibly survive.
Yes. So So now we have to do more careful.
Yeah. Okay.
Okay, so yeah, so this is what we want to do. So yeah, so to do this, what I'll do is we'll do some exercises with determinants, kind of, and then again like elementary exercise, and then we'll combine them and get this result. Okay, so let's start doing some exercises with determinants. So the first one is the following, that so exercise 1. Let M be an arbitrary square matrix. Okay, and define sigma k of M to be sum over all subsets, arbitrary square, let's say n cross n matrix. So S is a subset of size k, and then I look at the submatrix of M corresponding to those rows and those columns corresponding to S, right? So this is the sum of all the k-sized minors corresponding to. Okay. Then the first exercise is that determinant of xi minus n is exactly x to the power n minus k. K goes from 0 to n times minus 1 to the power k sigma k. Is this easily to see for everyone, or should we think about it for a little bit?
Just wait, sir.
Sorry?
Just wait for a minute. Let me think.
Sorry? So this is just so the only way to do this is to just expand and then you see this. So
the kth symmetric sum of the eigenvalues will somehow
that is one way of doing it, but the simplest way is just algebraically expand the definition of determinant and then you see it, right? So let's just do this. So what is this? Det xi minus m is
So M has zeros on the diagonals?
no. So zeros on diagonals, then it's easy. But the point is that even if it's not zero on the diagonal, still it works. So let's just. So this is what it is. So what is this? So let's say that sigma sin n. So let me just break it up into by fixed points. So, so yeah. So yeah. So I break it up on the so T is a subset of fixed sigma. So fixed sigma is a set of fixed points of sigma. Right? That's a clear relation. So yeah, okay. So on yeah. So these are the things where I choose X. So these are the only places where I can choose X. If I choose X, it better be a fixed point of sigma, right? Otherwise you cannot. And on the rest, I just do, yeah. So,
Here also there is this cancellation thing that will happen. Right?
Sorry.
No, it's no cancellation. No, it's just I see. Okay.
No. In the original formula, you sort of don't care about S and like when you write determinant of S,
Yeah.
S cross S, you also the fixed point set can go up. So that
That's the point. I mean,
cancellation.
so the thing is, yeah. So all I'm saying, yeah, all of this is just an exercise into going. Oh, yeah. So I agree that so they're fixed. So there are points that are. So even some fixed points can contribute things from M, but then you sum them up also.
Yes.
So
Yeah, so this fixed points are contributing to M when you're summing up, and yet somehow you're getting only the determinant.
Yeah, because the rest, yeah, I mean, you just move it into the, yeah. So
you move it into the rest, is it?
Yeah.
So
Yeah, so let me just,
but in the rest, you're having no fixed points, right? That's the assumption.
Yeah.
Okay. Right. That's where you move it to the rest. I see.
Yeah. So the point, yeah. So those also come back in because they don't contribute to the sign of the permutation. Right? That's the whole thing.
But I'm worried about the fact that you're summing over all. Now, when you're in the rest n minus k part, you're summing over permutations which are not, I mean, which are derangements, right? There are no fixed points.
Yeah, that's fine. So let's just.
Then why should you get determinant of?
No. So yeah, let's just do this. So yeah, so T is a fixed point. So mi sigma I not in T. So this is sigma. So it's just so this is fine, right? So let's just think about this for a minute. So I have summing over all permutations, sign of sigma, then summing over all subsets of fixed point of sigma. Now each subset. So what am I doing here? So I have this product to expand, right? So the only excess can come from fixed points. So I'm just summing over all possible things where I choose x. Like I'm basically the T is indexing which subsets, which of the terms did I choose x from. So I choose x to the T. The remaining will contribute mi sigma I with a minus sign. So that's why there is a minus 1 to the power n minus T. Okay. So far it's fine. Okay. So now let's change this. So let's take T to be a subset of n. Now I have to choose all those sigma in sim such that sigma I is, so it is that T is a subset of 6 sigma. Okay. And then I'm looking at sine sigma x to T minus 1 to the power n minus T product I not in T m I sigma I. Okay. But what is this sigma in sim and T is in fixed sigma?
Why is it I in sigma? Isn't it I not in?
Sorry, yeah, I not.
I in T, I not in T.
Yeah. So these sigmas are completely given by arbitrary permutations of n minus T, right?
Right.
So, and they have the same sign.
So this is like, yeah.
So two things happened here. The sign, so notice that sign didn't change because only fixed points were ignored. Okay. But this guy is by definition. So this thing inside, I take the minus into the, so this is T subset of n. Is this, by the way, all of this is, there's no x to the T. This is just side T. So now I have this minus 1 to the power n minus size of T, x to the T. And here, what is this thing that is remaining? It's exactly the determinant of m of T complement. So T complement, which is exactly what I wrote earlier. So okay. So this is this exercise was easy, right? So now, so this at least suggests that understanding the sigma k of m is a good goal, right? And since the matrices we are considering are all some, like they have good, like I mean, matrices, sum of rank one matrices, but we know some kind of a decomposition of them as sum of rank one matrices. So let's also use that. Let's try to understand that. But I'm running out of time because there's just 4 minutes left. So maybe I'll start this next time, and I'll stop here. And if there are any questions, you can ask.